Restarting a rocket engine mid-flight is not like turning on a car. In the vacuum of space, propellants float freely, making ignition exceptionally difficult. Without gravity to pull liquid downward, propellants disperse inside fuel tanks, meaning standard feed lines risk swallowing gas pockets instead of liquid fuel. Starship relies on 6 powerful engines, combining 3 standard Raptor engines and 3 Raptor vacuum variants designed specifically for deep space operations. The Raptor engine is powered by liquid oxygen and liquid methane, operating in a strict 3.6:1 mass ratio. According to official documentation, the nominal operating condition for the Raptor engine requires an injector face stagnation pressure of 3669.5 psi. Utilizing a sophisticated full-flow stage combustion cycle, the engine achieves phenomenal efficiency and delivers twice the thrust of the Falcon 9 Merlin engine. This enormous power output allows the vehicle to carry heavy payloads while managing complex thermal dynamics across all 33 Super Heavy booster engines. On May 22, 2026, the 12th flight test of Starship demonstrated the historic first operational flight of advanced Raptor 3 engines in actual flight conditions. During this ambitious flight, one of the vehicle's 33 Raptor 3 engines shut down prematurely, yet the rocket successfully achieved its planned trajectory. However, during the critical boost back burn phase, not all intended engines ignited properly, and those that did fired for less than 20 seconds. Restarting engines in the harsh vacuum of space requires overcoming fluid dynamics where propellants slosh and separate without the benefit of planetary gravitational pull. Before every in-space relight, Starship must carefully settle its cryogenic propellants using specialized maneuvers to force liquid reactants down toward the engine feed lines. Small RCS thrusters provide the necessary initial acceleration, creating artificial gravity that pushes liquid methane and liquid oxygen into the primary engine inlets. Inside the main propellant tanks, dedicated header tanks hold the specific fuel volumes needed exclusively for landing maneuvers and in-space restarts. Maintaining liquid methane at -161 degrees Celsius requires advanced thermal insulation and precise pressure regulation before ignition sequences begin. Once propellants are firmly settled against the feed lines, the engine initiates its complex pre-burner cycle using electronic igniters and precise valve timings. Dual turbopumps spin up rapidly to immense rotational speeds, pressurizing reactants to meet the stringent 3669.5 psi operating standard. Liquid oxygen and liquid methane enter the main combustion chamber simultaneously, maintaining the vital 3.6:1 mass ratio for optimal burn stability. The combustion chamber and nozzle are regeneratively cooled by circulating cryogenic fuel through internal channels before it enters the main combustion zone. The most visible change in Raptor 3 is not just the thrust figure, but the complete disappearance of the complex external plumbing look from earlier variants. SpaceX's design comparison highlighted how Raptor 3 replaced the old Christmas tree appearance by folding external complexity directly into the primary engine structure. To achieve rapid reusability, engineers removed external heat shields entirely from Raptor 3, utilizing advanced material casting to protect critical components natively. By routing internal channels through cast manifolds, SpaceX dramatically reduced part counts, leakage points, and assembly times for mass production. Every design iteration moves Starship closer to true airline-like reusability, allowing quick turnaround times between orbital flights and deep space missions. Beyond Earth orbit, reliable engine relights are vital for lunar missions, prompting rigorous testing for the human landing system version of Starship. SpaceX recently fired one of its Raptor engines to test its ability to land the giant Starship vehicle on the Moon in severe cold conditions. Landing on the lunar surface requires precise throttle control and absolute ignition reliability, as there is no atmosphere to assist with aerodynamic braking. During interplanetary transit between Earth and Mars, second ignition capabilities allow spacecraft to perform critical trajectory adjustments and course corrections. Liquid methane offers major advantages over traditional propellants, including easier storage in space and the potential to be synthesized directly on Mars. Executing orbital insertion and circularization burns demands flawless timing from the propulsion suite, ensuring safe and predictable spacecraft positioning. Overcoming fluid instability in zero gravity remains one of aerospace engineering's toughest hurdles, solved through clever tank pressurization and settling burns. Autogenous pressurization systems use boiled-off propellant gases to maintain structural rigidity in the tanks while forcing liquids steadily downward. High-response pneumatic and electronic valves control the massive flow rates required by the Raptor engine during startup and shutdown sequences. Ensuring spark-free or electronic torch ignition in a vacuum requires multiple redundant systems to guarantee the engine lights successfully every single time. Each successive flight test provides invaluable data on engine performance, thermal limits, and relight reliability under real spaceflight conditions. When premature shutdowns occur, SpaceX engineers analyze flight telemetry down to the millisecond to refine software and hardware parameters for future flights. At Starbase in Texas, automated tooling and high-rate manufacturing lines turn out Raptor engines at an unprecedented pace to support the massive fleet. Before flying, every Raptor engine undergoes rigorous static fire testing at SpaceX's sprawling development and test facility in McGregor, Texas. The combination of liquid oxygen and liquid methane delivers clean combustion with minimal soot buildup, significantly simplifying engine refurbishment between flights. Custom superalloys developed by SpaceX withstand the extreme temperatures and pressures inside the Raptor combustion chamber without degrading. Maintaining the exact 3.6:1 oxygen-to-fuel ratio requires high-speed digital controllers, adjusting propellant valves thousands of times per second. Acoustic cavities and precise injector tuning prevent destructive combustion instabilities that plagued early liquid-fueled rocket engine designs. Achieving routine orbital relights unlocks the full potential of Starship, enabling satellite deployment, orbital refilling, and interplanetary exploration. Transferring cryogenic propellants between spacecraft in zero gravity requires sophisticated transfer lines and thermal management to prevent boil-off losses. With Raptor 3 pushing performance boundaries, the Starship system stands ready to transform humanity's access to the cosmos and deep space destinations. SpaceX's rapid test-fail-fix development cycle allows engineers to iterate on Raptor designs faster than any traditional aerospace program in history. Removing heat shields and simplifying internal plumbing made Raptor 3 remarkably lightweight while retaining its massive thrust capabilities. While external shields were removed from the engine itself, integrated cooling channels ensure the metal can endure extreme combustion temperatures safely. Every successful test brings engineers closer to mastering the intricate physics of zero-gravity relights, securing Starship's operational future in deep space. As flight tests continue to validate hardware and software improvements, the secret second ignition of the Raptor engine ceases to be a mystery. Mastering in-space restarts opens the door to lunar bases, Martian settlements, and sustainable interplanetary travel for future generations of explorers. The evolution of the Raptor engine stands as a monumental triumph of modern aerospace engineering, combining raw power with sophisticated control systems. Through ullage burns, header tanks, and precise valve timing, SpaceX has turned a formidable zero-G physics problem into a routine engineering solution. By discarding conventional design constraints and embracing radical integration, Raptor 3 redefines what is possible in modern rocket propulsion technology. With successful cold-conditioned ground tests completed, the stage is set for Starship to land American astronauts back on the lunar surface. Every flight test, whether flawless or challenging, provides the critical empirical data needed to perfect orbital relights and guarantee mission success. From the daunting challenges of zero-gravity fluid dynamics to the streamlined brilliance of Raptor 3, innovation continues to drive space exploration forward. As Starship prepares for its upcoming orbital missions, the mystery of the second ignition has unlocked a new era of fully reusable spaceflight. Conquering the vacuum relight challenge proves that even the most stubborn laws of physics can be overcome with brilliant engineering and relentless iteration. With every engine test and orbital flight, SpaceX moves closer to making multiplanetary life an achievable reality for all of humanity. What aspect of Starship propulsion excites you the most? Drop your thoughts in the comments below and subscribe for more deep dives into aerospace engineering.